Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. In this problem, we have a coil of wire that is attempting to be rotated in an external magnetic field while that loop of wire has a current running through it. Now, let's look at a top-down version of what's happening here. So we have a north and south pole of a magnet, and therefore we have a magnetic field heading from left to right, like this. And we have a loop of current. I'm going to draw it from the top here, around like this. And that is put on an axle as it spins around. Now, in our diagram, we have the current heading up and out of the page on this side of the loop, and the current is going to be going down and into the page on this side of the loop. Now, if that's the case, then the normal that we're going to pick for this loop here is going to be heading off in this direction here. So that is our normal to our loop, normal to the cross-sectional area of that loop. So what is going to happen here is that this coil is going to try to rotate around clockwise in this external magnetic field when it's carrying a current through it. Now, the question we're ultimately asked is that if we're able to put a brake pad on this axle here, what is the minimum normal force we're going to need in order to keep this coil from spinning? Now, why is it trying to spin in the first place? We have to ask ourselves. Well, it's because the magnetic field is causing a torque on this loop because it is carrying a current, right? And that is given by the number of loops in the coil, the current flowing through the coil, the cross-sectional area of that coil, the magnetic field through which that is going through the coil, and the sine of the angle between the normal, what I've labeled here, right, and the magnetic field, the external magnetic field. So, and we've determined, right, that this torque is trying to cause this coil to rotate clockwise. And so we'll generally call this a negative torque. Now, we're going to try to keep this thing from spinning. So I'm going to redraw the axle on which the coil is put, and then I'm going to draw a brake pad touching that axle. So we're going to apply this brake pad here at a distance little r, the radius of the axle, from the axis of rotation or the pivot point, right? The coil is pivoting about this point. And that means if my axle is trying to rotate this way, then this pad is going to provide a frictional force in the opposite direction here. And because we're trying to find the friction force that keeps this coil from moving, it's going to be a static frictional force. Now, we're asked to find the minimum normal force that's required for this to happen, right? So if we push this brake pad onto this axle, what's going to happen, right, is going to be applying a normal force between the pad and the axle. And we know that for the minimum force required, right before this force, static friction force, would break down into kinetic friction force, we know that it's equal to the coefficient of static friction multiplied by the magnitude of the normal force between our brake pad and our axle. So we have to figure out what torque is caused by the static friction force, and then we can see how it needs to relate to our torque from the magnetic force in order for our object to not spin at all. So we know that by definition, torques are given by torques are given by thinking about how far away from the pivot point is our force being applied, which is we call an R, and we're going to multiply that by the part of our force that we care about that's causing the torque that is perpendicular to that radius here. So we see here our distance is just r, we know that value, and our static friction force is completely perpendicular to our radius r. We'll notice here right there. So all of the static friction force, mu s Fn, is going to be contributing to the torque. And so this is going to be the torque from our static friction force. And now we have to compare it to the torque from our magnetic force here. If we want our object to remain at rest, so we do not want this thing to rotate, then we want our torques to be equal to each other. And that is the main thing we're going to solve here. And because we want our static friction force to be able to handle the maximum amount of torque that is going to be exerted on this coil. Remember, right, the torque varies as it rotates because it goes as sine phi, right? So as the angle between the magnetic field and the normal changes, the magnetic torque will change. But if we have a normal force, so a normal force that causes static friction force that's large enough to handle the maximum magnetic torque, then it's going to be able to handle any magnetic torque. So really, we want to compare the torque from static friction to the maximum possible torque from the magnetic force, which to get a maximum possible torque, right, our sine phi value is going to go to 1, which means we have a phi of 90 degrees. So the torque, again, is going to be the maximum when the sides of our loop, our coil, are actually aligned with the magnetic field, and therefore the normal itself is perpendicular to the magnetic field. So those are the two torques we want to compare, and because we don't want this thing to move, we want them to balance. So let's write out the torque expression for the magnetic field. It's the number of coils in that loop, multiplied by the current through the loop, times the cross-sectional area of the coil, multiplied by the magnetic field that is in the coil. That's the maximum amount of torque that can be caused by the magnetic force, and we want that to be equal to the torque that's going to be caused by our minimum static friction force. And we want to find the normal force that is needed to cause this balance to happen. So we're going to solve for that value here. We have NIAB divided by the radius, right, of our axle, and divided by the coefficient of static friction. So how many, I think I called this just a loop of wire in the beginning. I'm sorry, it's actually a coil with current through it. So how many turns do we have in this coil? 410. What is the current through it? 0.26 amps. How is the cross-sectional area? 3.1 times 10 to the negative 3 meters squared. The magnitude of our magnetic field is 0.23 teslas. Going to divide all this by the radius of our axle. That's given as 0.012 meters. And we have a mu s, or a coefficient of static friction, of 0.76. Put all that into our calculator, and we see that the minimum normal force that we need to keep this coil from rotating in this external magnetic field is about 8.3 newtons. And that is our answer.